Okay, so let's review a little bit about what we learned last time. So we learned that there is a nice and simple three-term recurrence for orthogonal polynomials. So if we have linear functional with orthogonal polynomials, then we can always consider monic orthogonal polynomials, and the monic orthogonal polynomials satisfy these three-term recurrence like this, where b, lambda are some fixed sequences. And yeah, we also showed how to compute these b's and lambdas, the recurrence coefficients, using Henkel determinant and things like that. And what we are going to do today is that the recurrence, so the theorem says that orthogonal polynomials satisfy the three-term recurrence, and the converse is also true. So that's what we are going to prove. So it's called Favard theorem. So Favard theorem is a nice converse of the theorem that we just saw. So the theorem is called Favard theorem. So this sequence is indexed from n greater than or equal to 0, and lambda, the sequence where n is greater than or equal to 1. So these are sequences of, say, complex numbers. But we have to have this condition. Lambda n must be non-zero for all n. And let Pn be the sequence of polynomial be given by, so if you define this by a three-term recurrence, then it's uniquely determined. So we can say that this is a definition of the sequence. And greater than or equal to, say, 0, where the initial conditions are P0 is a monic, so it's 1, and minus is just 0. Then you can compute P1 using this formula, and so on. Okay, so the statement is that there is a linear functional L such that Pn is OPS if and only if I think this is not what I wanted to say. Sorry about that. Let me. Yeah, I didn't want to say this before. Okay, let's copy this. Cut. Yes, just a sequence of polynomials. Be a sequence of polynomials, monic polynomials, say. And you remember, we always assume that the degree is n, so I don't write that here. Then the statement is that this is OPS if and only if Pn satisfies this, where lambda n non-zero. Yeah, of course. Oh, okay. I'm sorry, I think I messed up. Yeah, I start over here. Yeah, sorry about that. Yeah, I didn't want to write this all the way over here. Okay, sorry, I'll start over. let's have a fresh start here. So theorem, Farfara theorem. This is very important, so I think it's worthwhile writing this twice. So P and X, a sequence of polynomials, monic polynomials. Then there is a linear functional L such that P and X is OPS for L if and only if they satisfy the three-term recurrence. So Pn plus 1 where Bn, lambda n are sequences and lambda n non-zero. Okay. So yeah, that's what I wanted to say. For some sequences, Bn, lambda n with this. Okay. So let's prove this. Proof. We already proved one direction, right? We proved that if this is really an OPS, then we show that they satisfy the three-term recurrence like this. So this direction is we have done this. We have already done this. Right? So we only need to check the other direction, okay? So, so we have OPS, we have a sequence of polynomials satisfying this three-term recurrence. And we want to show that there is a linear functional for which these are orthogonal. But if you think about the orthogonality, then you don't really have much choice for the linear functional. You have really, the linear functional is kind of very restricted. So to do this, suppose that it is really an orthogonal polynomials. There is, I mean, this is a little weird, but if there is such L, then what happens? Then we must have orthogonality says L of Pn times Pm equals 0 unless n equals m. So in particular, Pn x must be 0 for n greater than or equal to 1, right? Because this is, imagine that P0 is multiplied there. P0 is 1, so therefore, L is uniquely determined and if n equals 0, this must be non-zero. So if you say that L of Pn x equals delta n 0, then for all n, then the linear functional is completely determined. So by this, we don't have much choice, but we have only one choice. We have to really define the linear functional this way. And then we just hope that this is the right linear functional. And we need to show that this really satisfies the linear function, the orthogonality. So we define a linear functional L by this equation. So this is the definition. We just define it that way. There's no, we can just define it that way because this will give us what the value of this, and also it will tell us what x is because we know P1x, and then using expanding this as a linear sum of moments, then you get mu1 and then you get mu2, etc. So all the moments are determined, so the linear functional is defined. So we need to show what? That this really gives us the orthogonality for the orthogonal polynomials. But there are several ways to do this. X to the k, p and x is 0 if k is less than 4, 0 kn. This is delta kn something non-zero, right? Because this is the equivalent condition for orthogonal polynomial. But we actually know what this k, capital K should be. So we will, in fact, prove this. And because these are these are all non-zero by assumption, so this is enough. Okay, maybe we need to show that. I think it's better to say it's enough to show. Enough to show this, right? Because of the theorem that we had before. So how can we prove this? We will prove this using by induction on what? Not n, but on k. We will prove this by induction on k. What happens if k equals 0? So k equals 0, base case. Then we need to show this. P and x, this is 0 unless n equals 0. N equals 0 is 1. So this is the same. Here is empty product, so this is assumed to be 1. So this is true. So it's true. Okay? So k equals 0, the base case is easy. And for the inductive proof, let k greater than or equal to 1 and suppose, let's say, a claim. Claim is true for k minus 1 case. Okay? And then we will show that it's also true for k. So to do this, because n must be greater than or equal to k, consider an integer n, and then we will show this. But to do this, we will use this recurrence. So multiply. Well, you see, this, if you want to look at this, that can be obtained by this if you multiply x to the n minus k minus 1 there. So multiply x to the k minus 1, both sides of the equation, the return recurrence, and taking L, what happens? Okay, let's take the linear function later. Then this gives us x to the, I'm going to rewrite this equation, x to the k, p and x equals, I'm going to move this, I leave this and then move the other terms out the other side. So x to the k minus 1, pn plus 1x plus bn x to the k minus 1, pnx plus lambda n x to the k minus 1, pn minus 1k, right? So this is the same thing as this with k x to the k minus 1 multiplied. So now taking the linear functional, we get, but if you take the linear functional, this will be 0 because of the induction hypothesis, because this is k minus 1. So this is 0, and this also 0, and this may not be 0. Okay, let me make some space. Lambda n, and this may not be 0. But by induction hypothesis again, this is equal to this n minus 1 if k is equal to n. So this is really by induction hypothesis delta nk lambda 1 lambda n minus 1. Because these two are equal, that means n equals k. So then that means still true. So by the induction we are done. So the claim is proved. So that's the proof. Okay. So. And note. This is L is positive definite if and only if lambda n greater than or equal to 0. So you can say that moreover the linear function is positive definite if and only if lambda greater than 0. So we already proved this, so I'm not gonna mention that again. All right, so that's the theorem of Favart. Now we will move on to the next section, and in this section, 2.5, it's about Christoffel Darboux identities and zeros of orthogonal polynomials. So using the three-term recurrence, we can prove these Christoffel Darboux identities, and they are identities very useful in the theory of orthogonal polynomials. And among many of the applications, we will see a nice property of the orthogonal polynomial, of the zeros of the orthogonal polynomials. So first, let's state the theorem. This is called the Christoffel Darboux. Oh, yeah, this is a typo. Darboux identities. So P and X polynomials satisfying the three-term recurrence. So Pn plus 1 x equals x minus bn Pn x minus lambda n Pn minus 1x. The usual way, like we always write, like n greater than or equal to 0, p 0, 1, p minus 1, 0. Yeah, I'm not going to repeat that. So of course, then they will be a sequence of orthogonal polynomials. You can find a linear function of that if lambda is non-zero. Okay, and which we will assume lambda n non-zero. Then we have the following two identities. First, summation k from 0 to n, pkx, pky. So we will use two variables, x and y. Lambda k equals p n plus 1 x, p n plus 1 y, n and y. And then we replace x, 1, y. We change x and y. X. Divided by lambda 1 lambda n x minus y. And second, as k from 0 to n, p k x squared over the same denominator equals p, let's have some space, prime, this is the derivative, Pn x minus Pn plus 1x Pn prime x over lambda 1 lambda n. So we have these two identities. So we will prove this. Proof. So let's call this star. So the idea is multiply a piece, because we want to get this, we multiply p and y over here, multiply p and y to this equation, then we get pn plus 1x pn y equals x minus pn x pn y is a simple multiplication. Maybe pn y pn minus 1x. Okay, it's nothing serious. And we will, because we also want this, but that's exactly this with xy, interchange it. So interchange x and y, then we get exact same thing with x and y replaced. I interchange it. So x becomes y becomes x. It's xy, the same thing, so I'm gonna write the same lambda n pn x pn minus 1 y, like this, okay? And just subtract these two, subtract, then we get pn plus 1x pny minus pn plus left hand side becomes this and x. And what about the right hand side? You see here this bn will be cancelled because they are the same. So x minus y multiply the same thing, pnx pny, right? And minus. So this is minus and plus, so I'm gonna write lambda n first, and then pn x pn minus 1 y minus pn y pn minus 1 x, like that, okay? Now you see this and this, they are almost the same, except n is just replaced by n minus 1. So let's say, for convenience, let's put this to be this. Let's use this notation so that we don't have to write this all the time. Then what happens? Oh, yeah. Yes. Question?
세 번째 줄에 람다의 앞에가 플러스로 되어 있지 않습니까?
I think you're right. Yeah, plus. Because this is my plus, minus plus. So yeah, I think that's right. Thank you. All right, then. Okay. Now let me rewrite this formula, and I'm gonna write this first. So then x minus y, pn. Oh, but instead of n, I'm gonna use k because I want to sum over this. So pk x pk y equals. So this is this with n, just k, n is k now, and this is what fn. So this is fk and minus lambda n fk minus 1. Okay. And then we're gonna divide both sides by both sides by lambda 1 dot, 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 lambda k and see what happens. Oh, and maybe this as well. Then we get p kx pky over lambda 1 dot, 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 lambda k equals fk over lambda 1 dot, 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 lambda k x minus y minus fk minus 1 lambda 1 lambda k minus 1. Oh, sorry, this is lambda k. So you see, these are really the same with k replaced by k minus 1. So if you sum this over k, there will be a lot of cancellation. So sum over k from 0 to n. Yeah, let me just be lazy and then say this. Sum over k from 0 to n, we get 1, right? Do you see? So basically we get k equals, so if k equals 0, this is going to be 0. That is just 0. There is no term like that. So we only have the last term, which is k equals n case, but that is exactly this. Okay, so that's the proof of the first identity. Where you can say f minus the 1 equals 0. Because here f minus 1 means, this is 0 and this is 0. So usually we get the first term and the last term, but the first term is 0. So we only have the last term. That's why we get only one term here. So the first identity is proved. So what about the second? This is basically this with x equals y. If you take the limit x equals y, we get this. But if you cannot just simply substitute x equals y because of this. But if you think about it, you can rewrite this so that it looks like a derivative. So let's rewrite the first term. Write 1 as follows. Instead of this, I'm gonna write maybe that's the usual technique that you do when you prove a product rule in calculus. So minus p n plus 1 y p n y. Because I subtract this, I have to add this again. So maybe I need more space. And plus pn plus 1y, pn, oh sorry, I wanted to have y minus p n plus 1y, oh, pn x. Now you see you have this common factor. So taking the limit x approaches, maybe y approaches x, we get the second identity, because this part, this minus this divided by this, is really the derivative. And also common factor, and then this, you get derivative. So that's how you get the second identity. So that's the proof. And like I said, there are many applications of this. You can also be one example being that we can find the measure of an orthogonal polynomial using Christoffel Darboux identities. And another one that we will do right now is that we can say a little bit, quite a lot about the zeros of orthogonal polynomials. So, in fact, we will show that the zeros of orthogonal polynomials, they all have real zeros, all distinct real zeros, and the zeros alternate if you increase the index of n. Okay, so I'll tell you more details. But let's first prove that the orthogonal polynomials have distinct real zeros. So that's going to be a lemma. So L, it must be a positive definite. So it's a positive definite linear functional. So we can consider monic orthogonal polynomials, OPS, say Pn. Then Pnx has n distinct real roots. For all n, of course, greater than or equal to 1, because P0 is just a constant. Oh, I think that's also true because it has no root, so yeah. But anyway, yeah, let's just consider n is greater than or equal to 1. So proof. Okay, first, since orthogonality Pnx, this is 0, right? Pnx must have a root of odd multiplicity. Why? Why is that? Suppose otherwise. Suppose that all the roots have even multiplicity. Okay. Otherwise, it doesn't have. It has only. Otherwise, it has like complex roots only or even multiplicities. That means P and x is always greater than or equal to 0 for all x. Because if you consider the graph for y equals P and x, then if there's no odd multiplicity roots, then they all stay above the x-axis. But then, by the property of the positive definite linear functional, this must be 0. This must be a positive, a contradiction. Okay. So it's going to be. So it has at least one root of odd multiplicity. Okay. So now let's say x1 dot 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 xk be the zeros, distinct zeros of Pn with odd multiplicity. We want to show that k is in fact equal to n. Then we will be done. Okay. So then, if you multiply x minus x1 dot 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 x minus xk to this, then this will always greater than or equal to 0, right? Right? Because again, the same argument. Okay? Because this is always greater than or equal to 0, so linear functional. positive definite must be greater than 0. In particular, this is non-zero. But what is the degree of this? This is a polynomial of degree k, right? So whenever you have a linear orthogonal polynomial Pn, if you multiply a polynomial of degree less than or equal to n, obviously k is less than or equal to n, this must be 0 unless k is equal to n. So by orthogonality, k must be n. Otherwise, it will be 0, this linear function. But what does that mean? That means these, we have n distinct roots, but that's what we want. So Pn has n distinct roots. So in particular, it only has real roots. There are no complex roots. Distinct real. Yeah, maybe I should say real zeros. So this is nice. Now we can prove this nice theorem. But okay. Same assumption. Yeah, so same assumption. Okay. Actually, I'm gonna include this in the theorem. I want to say and if so because these are this has distinct real roots. Okay, distinct real roots. Let's say x n n. I'm gonna write in this way. X in the n minus 1. I'm gonna order them according to their size. Sorry, it's n1. Distinct real roots and such that the zeros interlace. Maybe with interlacing property, let's say. That means x n plus 1, this is, these roots come in between like that. So x n n, x n plus 1 n, x n n minus 1, like this. And finally, x n plus 1, 2, x n 1, x n plus 1, 1, like that. So we will prove this. Okay, because of the space, I'm gonna move this to the next page. We already show that zeros are all distinct and all real. So this, so far, we have already proved. So this is the only thing that we need to show. And this is where we need the Christoffel Darboux identities. The second one, actually, the second Christoffel Darboux identity second. If we substitute x equals x and j, let's say, then see what happens. Then we get, I'm gonna just write down the identity where I just replace n by x and j squared, lambda 1, lambda k, like that, and equals p n plus 1 n plus 1, j minus p n plus 1 x n j prime x n j over lambda 1 lambda n. But this, what is this? This is a root of Pn. That means if you plug in this into Pnx, it will be 0. This is 0. This is 0. And yeah, this is 0. So, but this is positive, right? This is positive. This is positive because k0 is 1, so we have at least non-zero number there, so it's always positive. So in particular, so we can, so this is positive, so we can forget about this, and this is negative, so that means this is negative, that means p n plus 1 x and j has the opposite sign. Opposite sign, then that of, then sign of, let's say, opposite sign of, yeah. So their signs are different, all right? Okay, so now let's look at this more carefully. So it's helpful if you consider the diagram or the graph. So this is like x and 1, x, maybe I can just forget about this sign, and 2, like that. Let's say 2, 2, 2, x and n. Okay, so these are the zeros of Pn, and this is monic, so the leading coefficient is 1, so if x approaches infinity, it will go up. So the graph of y equals Pnx must be something like this. Okay, this is y equals Pnx, the graph of y equals Pnx. All right? So what is the sign of Pn? What is the sign of Pn prime x and 1? This means the derivative of this, but that means the slope of the tangent line. So it's positive. So this is positive. So positive, and this is negative, right? So positive and negative alternate. So the sign of Pn prime x and j is minus 1 to the j, actually, right? Oh, sorry, j minus 1. Because first positive, negative, so it looks like that. And this means that means the sign of Pn plus 1 x and j is minus 1 to j, because it's the opposite. That means if you substitute this into Pn plus 1x, you get something something below. Oh wait, this something over here. Oh yeah, that's right. You get something over here, and then it changes the sign, so it goes above somewhere here, and then down and up like that. So that means we must have, because this is a continuous function, we have to connect these two, and also we have to connect these two, and also we have to connect these like that, right? So that means one solution, one root in this interval, open interval, x and j plus 1, x and j, like that. So for j 1 up to n. n minus 1 actually. Yeah. So we found n minus 1 roots, but also if you consider the n x approaches infinity, limit x approaches infinity, Pn plus 1 is of course infinity, and it's negative version. This depends on the size, the parity of n, so I think it's going to be like that. That means we have 2 more roots like that, here and here. And they all alternate like that as we wished. So this is xn plus 1, 1. This is x1 plus 1, 2, like that. So that's basically the proof. So interlacing. Any questions so far?
맨 밑에서 두 번째 줄에
네.
마이너스 1에 n 플러스 1 승으로 되지 않습니까?
I think you are right. Yeah, this must be the same here, because P0 is, sorry, P1, it must be 1, yes, right, yeah, thank you. Yeah, so it changes, like, goes below or it goes above, like that, alternating. Any other question or comment? Okay, so these are like the basics of orthogonal polynomials. So far we haven't considered much about combinatorics. So from now on we will switch gears and consider combinatorics. And we will focus on focus on combinatorics of orthogonal polynomials. Okay. So that means if you didn't like the course material so far, it's a good news for you. You can basically forget about them. We only need some essential things like definition of orthogonal polynomials and three-term recurrence and basic notions like moments and things like that. I'm going to review these anyway. So our plan is, but because we need some basic knowledge of combinatorics, we will review basics of combinatorics. It's like generating functions, this is basically formal power series, so we will define the notion of formal power series. And we will consider some lattice path, like 2 important families of lattice path that we will need are Dick path and Mochkin path. We will see them later. And some basic fundamental object in combinatorics like matchings, set partitions, and permutations. These will all play important roles when we study orthogonal polynomials. So when we study orthogonal polynomials, there are roughly two ways. So there are 2 ways to study orthogonal polynomials. It's very vague, but and also quite trivial. General theory. So like what we have learned so far are general theory. So it applies to all orthogonal polynomials, like 3-term recurrence and stuff like that. But in the when we study orthogonal polynomials, we will also focus on special orthogonal polynomials. So like important families there are kind of classifications of classical orthogonal polynomials, and mostly we will be considering these orthogonal polynomials: Hermite orthogonal polynomials, and Charlier, and Laguerre, and there are more, of course, but we will focus mostly on these three because they have the nicest combinatorial structures. They're simple, so that we can understand them very nicely. And right. So, for example, if I tell you this, a little bit about them, what's nice about them is that for Hermite, we have moments, right? If you compute the moments of these polynomials, by moments of orthogonal polynomials, I mean that when we have orthogonal polynomials, there will be a linear functional, which will be determined uniquely if you set L of 1 equals 1. So we have linear functional, so we can talk about the moment, L of 1, L of x to the n. Then the moment, mu n in this case, actually it only has even moment, so it's a symmetric orthogonal polynomials. It's 2n minus 1 double factorial, which means like 1 times 3 times dot 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 2n minus 1. And Charlier, yeah, there's a formula, but not close formula like this, but there's a nice combinatorial formula. This is n factorial. So if you look at this is the number of perfect matchings on 2n. Okay, let me erase this. Combinatorial meaning. Combinatorial object. So perfect matchings. Here it's going to be set partitions. This is exactly what I wrote over there, set partitions. And these permutations. So we will learn Vienno's theory, and this will allow us to express moments using Marchkin path. And using this general theory of Vienna, if you apply that Vienna theory to each of these, each time you get very nice combinatorial object like perfect matchings, set partitions, and permutations like that. So this is what we are going to do for the next few weeks. And after that, we will learn more combinatorial structures of orthogonal polynomials. But, yeah. So I think today I'll finish here. And there's a announcement. There will be no offline class on Tuesday this week, because there's a university festival, so I will... Thursday? Oh yeah, sorry, Thursday. So yeah, 2 days from now. So I will upload a lecture video on the web page, so you can just watch the video. And we will resume next Tuesday. And actually one more, there is a homework set available. Due is next Thursday, so also available in the web page, so please check that out. So, okay, so I'll finish here. Thank you.